Hello students, in this video we'll define the notion of what it means to have a subset of a certain set. If we're given a set A, then we say that B is a subset of A if for every little b in the set B. And so here this notation, lowercase epsilon, that notation means is in. So little b is in the set B, implies that for every little b in B, we have that little b is also in A. So no matter what point I choose in the set B, it must also be in the set A. And so what we'll do is we're going to write the notation we're going to use for this subset. Notation. We'll say that A is a subset of B. So we have this backwards. So we're going to say B is a subset of A. So B is a subset of A. And we have one thing to consider with this notation, so there's a little bit finer refinements of this. If B is a subset of A and B is not equal to A, not the whole entire set A, then we can write B as a subset and with a little slash to that equal sign over there. B is equal to A, and we can call B a proper subset of A, and say that B is a proper subset of A. So let's see some examples of this. So if we can define, so let's let B be the set 2, 4, 6, 8, etc. Namely, B is the set of even integers. And let me let C be the powers of 2. So we'll have 2, 4, 8, 16, 32, 64, the set of powers of 2. Well, it's clear that we can see that if little c is in capital C, then C equals 2 to the k for some k greater than 1. But what that tells us is that C is some multiple of 2. And that implies that C is even. And I can write C being even as saying i.e. That's the same thing as C is in the set B. So we've proven here that the set C is a subset of B. And now we can notice, so note 6 is in the set B, but 6 is not in, we'll put a slash with that E, so we'll do this slip. This will be not in, is not in the set C, which means that C is a proper subset of B. And so two things to note about this is just a remark. So remark, B and C are infinite cardinality. They have an infinite number of elements. And they're both countable. We won't prove that, but we'll just assert that they're both countable. It's actually fairly easy to prove. But the point now is that we see that it seems that the set C is much more sparse than the set B. In fact, we can see that they look like they agree for a little while, but then I'm going to get 10, 12, 4, I'm going to miss 10, 12, and 14, and I'm going to miss 18, 20, 22, 24, 26, 28, 30, and there's lots of terms in B that do not occur in C, so C is fairly sparse, whereas B is fairly dense, but both these sets have a countably infinite cardinality, even though C is a proper subset of B. So we see this notion of infinite cardinality contains lots of sort of subtleties, and so while we won't study that, we'll just make allusions to the fact that this is a very complicated process to understand this notion of cardinality, but for us it suffices to show that these are subsets of each other. Thank you very much.